So, in physics, we've been talking about accelerations, and like with projectile motion, what happens to an object because it's got a gravitational acceleration that is directing it downwards. But why is that acceleration there? And the answer is that there is a force that is acting on that object to make it do that. So we're going to talk about forces, or we did talk about forces in class today. So, you have something called a force that is in newtons. That is basically something acting on an object. Usually we think about it as some kind of push or a pull. And that push or a pull will change an object's velocity. It will change either its speed or it will change its direction. And so what's a change in velocity? A change in velocity is an acceleration. And Newton realized stuff about this, and so he developed Newton's three laws of motion. Well, we call them Newton's three laws of motion because he developed them. And we talked about a couple of them today. The first one, Newton's first law, is also called the law of inertia, saying that an object will continue at constant velocity unless acted on by a non-zero net force. So what that is saying is if you have different pushes or pulls that are acting on an object, then if there is some non-zero resulting force of that, then an object will change its velocity, meaning either its speed or its direction. If there is no non-zero resulting overall force acting on an object, it will just keep on keeping on. It will keep on doing what it's doing. So it will either move in the same direction with the same exact speed, or if it's at rest, then that means it will just stay at rest. So a rock will stay on the ground unless you kick it, or unless something else happens to it to actually move it. Otherwise it will still be there until something happens to the earth. Okay. So it will really, it means constant velocity, meaning constant speed and constant direction. If, however, you do have a non-zero net force, then that means that you end up having a change in the velocity. And that non-zero net force will cause that change in velocity, which will cause that acceleration. And so that ends up as the second law, saying that non-zero net forces cause accelerations. That acceleration, then, which will be a vector as we've been talking about, is equal to the sum of our forces, meaning adding up all the forces together, and that's your net force. It'll be that net force divided by the mass of the object. Because the mass of the object is basically the proportionality constant that says how easy is it to move it. How hard is it to resist, how easily does it resist the motion, or how easily does it move? The more mass an object has, the harder it is to move it. The more it resists a change in motion. So the resulting acceleration has to be inversely proportional to that. And then the harder you push on an object, the more it's going to move. So it'll be directly proportional to that force. Usually, we don't write it as A equals F over M. We say that F equals MA. It's a more simplified, compact way of writing it, just because it's not dividing by anything. So, any net force is going to be equal to an object's mass times the acceleration it experiences. So this applies to some object with a mass that is experiencing an acceleration because of some non-zero force acting on it. Okay? And so if the sum of the forces is non-zero, you will get a change in velocity, meaning a change in speed or a change in direction. And yes, these are vectors, and so therefore you do have to worry about breaking up into components. So you'd have to actually look at the sum of the x vectors and the sum of the y vectors, see what those are, and then combine them together to get the full F magnitude would be the square root of fx squared plus fy squared. And of course, the direction at which the overall force is acting would be the inverse tangent of the y over the x, if you're doing the angle with respect to the x-axis. So this also means, from this equation, that the direction of the resulting acceleration an object experiences is going to be in the same direction as that net force, which makes perfect sense. If you're pushing on a box in this way, it's going to keep going in that direction. It's not going to all of a sudden veer off. Okay, that's not what you're doing to it. You are pushing it in that direction. And so its acceleration, its change in motion is going to also be in that direction. Okay. The other thing that we talked about today was to look at one specific example of a force, going back to the projectile motion idea, that we do have this gravitational force that is acting on us, and it is a force. So we experience the 9.80 meters per second squared acceleration downwards because of the fact that the Earth has mass and is exerting a gravitational force on us. So the force of gravity, in its full-blown form, is Newton's gravitational constant, or the universal constant, times the mass of one object times the mass of another object divided by the distance between them squared. Okay? So, if you have two objects, the force is directly proportional to the product of their masses. So the larger mass an object has, the stronger the gravitational force is going to be. And then the further away you get from an object, the lower the gravitational force is going to be. It's inversely proportional to that distance squared. That's a very important part, that distance between them is squared. So if we're looking at the acceleration at the surface of Earth, that due to gravity is negative g, so negative 9.80 meters per second squared. And we say that something has a weight because it's being acted on by the gravitational force. So the weight of an object is equal to its mass times the gravitational acceleration that it gets. Okay. Now we usually just have the weight be the magnitude, but it must be understood that if you were to draw the arrow for that force, it would be directed downwards, because we're being accelerated downward toward the ground, toward the Earth, because of Earth's gravitational force pulling us down. So it would actually be directed downwards. So if we're looking at the surface of the Earth, this equation right here has to equal this with specific things for Earth. If you're not looking at Earth, then it's just m times whatever acceleration this happens to be equals that. If you are looking at Earth, then that means that mg, m being you, whatever mass you are, is equal to capital G times your mass times the Earth's mass divided by the radius of the Earth squared, where we can and do place all the mass of the Earth at the very center. That happens because you have a certain attraction between you and the patch of ground right below you, and that is much stronger than the attraction between a patch of Earth on the exact opposite side of the Earth from you and that patch right there. And if you average all those attractions out, it works out for it to be at the very center of that spherical body that is the Earth. So, this would be the mass of the Earth, that would be the radius of the Earth. These masses would cancel, and you get that g, or 9.80 meters per second squared, is arrived at from these constant values. Newton's gravitational constant, the mass of the Earth, and the radius of the Earth, squared. So if you put those in together, you end up with 9.80 approximately, which of course will vary on the surface of the Earth depending on where you are because of bumps, hills, whatever types of materials below you. You'll have different densities that will change this a little bit. But the basic overall number is derived from this because it is a force, and so therefore causes an acceleration on you. The acceleration being g, 9.80 meters per second squared, which is directed downwards. And so in next class we'll talk about Newton's third law and get at dealing with all these forces and how to think about that with more ideas of the vectors and lots of applications.